I'm picking up background noise from you, Brandon, just a heads up.
I'll... Okay. See if that fixes it.
Alright, I'm gonna head into the giant members voice. Unless you need me here. Head into the giant members voice. Unless you need me here. Head into the giant members. Audio's coming through on the black screen, just FYI.
Is that from me or you?
I think it's you. I don't know who's. Can anyone hear me? Hello? Hello?
I think he has audio output set up.
Hello?
I think he has audio output.
Yes, we can hear me.
Oh, okay, cool.
So we're good. We can go live whenever.
Alright, I'm gonna start it then.
Go for it.
Welcome to cryptography, day 1. I'm Brandon. I'm a third-year computer engineering student at Purdue. My primary interests in security are cryptography and reverse engineering. So for how it's going to work for today is we'll go through classical cryptography because it's a nice place to start. It's not too difficult. The math is pretty simple. So we'll go through some terminology, substitution ciphers, and then we'll look at how we can take the substitution cipher and relate that to modular arithmetic and then introduce some concepts there. We'll go over XOR and how to interpret different data representations. Just because sometimes when you're playing CTFs, you'll be given a ciphertext in hex, and it's just helpful to know how to get that to something that you can work with in Python. And then I'll also preview day 2 material that I'll be going over on Friday. So for classical cryptography, we're going to start off with a question for the audience. Are you guys familiar with cryptography, and what do you guys know? Yeah, so people will usually refer to as crypto as a cryptocurrency, and while there's implications of that, that's not entirely what we'll be focusing on. So how familiar are you guys on a scale of 1 to 10 with cryptography? Like, have you taken a course in it, or have you like self-studied it? That's good. I see some people are saying they're familiar with RSA. I'll touch on that at the very end of the presentation, more as a preview of what we'll go through on Friday. But that's good that you guys have seen these things before, so the transition won't be as difficult if you're coming from no background. But I'm going to try to make it easier for everyone so that we can all learn something from this. So we'll first start off defining a few terms. So typically we have what we call our plain text. It's what we're looking to encrypt. Examples could be credit card number, your SSN, social security number, if you didn't know what that acronym was. So we want to send this over, ideally the internet, as some sort of protocol, and we want it to be transmitted such that the other party will receive it, but anyone in trying to retrieve the message in between isn't able to grab that and take our information from us. So when we're dealing with encryption, we'll have some sort of function, and the output of that function is the ciphertext, which ideally when someone intercepts the ciphertext, you want it to be, you don't want any sort of similarities between the ciphertext and plaintext such that you're able to decrypt it in that fashion. So then as I said before, here we call the encryption function E, and it's the way we're going to transform the plaintext to the ciphertext. And inversely, the decryption function D is the method that we will use to transform the ciphertext back to the plaintext. You can think of it as like the inverse of the encryption function. So for substitution ciphers, I'm going to term the plaintext alphabet as P and the ciphertext alphabet as C. And what we're looking to do here is we'll take our two alphabets and we're going to have like a one-to-one mapping between them, so that when we encrypt, we will take the corresponding letter in the ciphertext alphabet and swap it with the plaintext alphabet character, and then that's how we'll end up grabbing our ciphertext. So in this example, I'm using the alphabet as our plaintext alphabet, and the reverse of that, so Z to A. So the way I explained it through a more math way is we're going to take an element X from our alphabet P, an element A or an element Y from our alphabet C, and then the encryption function is as follows. It's essentially you're going to correlate the A here to the Z here. So if you encrypt A, you'll get Z. If you encrypt D, you'll get A, or Z, you'll get A, my bad. So it's sort of a reverse in a sense. So when we look to encrypt more than one letter, you'll just do it one by one. So H here corresponds to the S here, the E corresponds to the V here, and so on. So then decryption is going to be pretty much the same way, except we'll go from the ciphertext alphabet to the plaintext alphabet. So we'll take the S here, and that'll correspond to the H here. And same thing for V will become E, and then as you can see we have hello, and then SVOOL is its corresponding ciphertext. So if you weren't aware, this alphabet and ciphertext correspondence is actually the @bash cipher, which is it's just the reverse and the normal alphabet used in place. So now I'm going to introduce the Caesar cipher. which is somewhat similar, but not exactly. So with the Caesar cipher, what we're looking to do is take our plaintext alphabet, which will be A through Z again, and we're going to shift it a fixed amount to the left or right, and then based on that, we'll be able to obtain a ciphertext when we input our plaintext characters. So visually what it's going to look like is if we use the shift of 13, A will become N, B will become O, C will become P, D will become Q, and so on. So you might be wondering what happens when we have a letter towards the end that when we shift won't necessarily fit. If you think about it, might shift and become out of bounds. So what we do in that case is we are going to think of it as like a circular object. We're going to shift it back to the front. So in that case, when we shift these elements, which would be shifted out, we'll obtain where S is F, T is G, and so on. So this kind of visually is demonstrating what modular arithmetic is. What we're trying to do here is wrap it around so that we can still retain what we previously had as an alphabet, but still form a encryption ciphertext. So what this is going to look like with a more math approach is we are encrypting with a right shift. So we have the letters A through Z, which will correspond to 0 through 25. Why I chose A as 0 might not be clear now, but once we continue going through it, it'll be more clear. So when we shift by 13, we're going to call that shift N, and we'll take our plaintext character for each character in the string, and we'll call that X. So expressing that as a function of E, or expressing E as a function of X, we can say X plus N mod 26. And then decryption equivalently would be the result of E, where we subtract N and take mod 26 of that. So in the case that you were shifting to the left, you could instead subtract by N and add by N for decryption in that converse case. So you might be wondering, what is a mod 26? You may have not seen that before. So mod 26, if you haven't seen it before, is the percent sign in a lot of languages like Python. It's the remainder from when we divide a number. So like 5 mod 2 would be 1, because 5 divided by 2 will fit into 5 twice. The remainder of that will be 1. So that's how we're going to explain mod as the remainder of division. So then the reason why we have A as 0 in this case, so 26 mod 26 would be 0. So when we shift everything by 1, Z would become in the same spot that A was in the plaintext. So that's why we're choosing that to be 0, and why we choose 26 to be our modulus, because that's given the size of our plaintext alphabet. So with modular arithmetic, we have what we call the modulus, which is N. And then we have this weird symbol, 3, it looks like a triple equal sign, I guess you could call it, with 3 bars rather than 2. So what that means is that the number A is congruent to B modulo N, as I put in the quote underneath. So the reason that we're using modular arithmetic is because different operations and properties that are present within this type of math makes it a much harder problem to undo or break, which is not true of other forms of math that we could use. So, and that's the whole basis of cryptography, is that we want to introduce problems that are hard to break, so that people that intercept said ciphertext can't easily undo it without some sort of more complex approach to breaking that system. So for our, so I'm just going to go into a few examples of modular arithmetic, more along the lines of congruence and what it means and how we're going to explain relations between these. So if we have 17 and we take mod 5, we'll obtain 2. You can check that with Python. I'll show it in Python in a few moments after I do this slide. But we can express this as a equals k times n plus b. And you'll notice that if we're dividing 17 by 5, we can fit 5 within the 17 3 times with a remainder of 2, which is how we're obtaining this result of 2 as the result of taking mod 5. And similarly, if we're dealing with negative numbers, it's a pretty similar approach because we're going to add or subtract, in this case, a scalar multiple of the modulus, which is 5 again. So with the integer negative 17, we can subtract by 20, which is negative 4 times 5, adding 3, which is our remainder in this case, which is where we're getting 3 from. So you might be wondering, where am I getting this a equals kn plus b? As I said, it's another way of sort of expressing division, or long division, I guess you would say. Maybe you're familiar with that from like grade school. So with long division, we're looking for how many times does this integer n fit into a? What's the number of times? That in this case would be k. And then the remainder in this case would be b. So when we say a mod n, we're saying how many times can we fit n into a? We'll fit that into that many times, which is k sub 1. And then if there's a remainder, it'll be r. Same case here, we're saying how many times does n fit into b? So that will term as k sub 2 with a remainder of r. And a thing to note here is that since a and b are congruent, we're going to have the same value of r as our remainder, because so in the case of this, we're keeping r kind of fixed here, and we're seeing how many times can we fit this in. So at the result, our r value will retain what it was, and we'll get unique values, assuming they're not, well, they can be or not be unique, they could be the same, but we'll get those two values for k1 and k2. Finding those, we can subtract these two equations, and then here in this case, our k would be k1 minus k2 times n plus b. So then now we're going to move on to looking at representation of data in Python and just in general when you're solving CTF challenges. So we have binary, which is base 2. It's just another way of counting. Most of us are used to counting in base 10. So in base 2, we're only looking at zeros and ones. So rather than when we normally count, it's 0 through 9. So what this could look like is just 1, 0 repeating. This is stream offline.
You're good.
Oh, okay. So did everyone catch that prior portion, or should I repeat anything?
I think you're good.
Okay, so yeah, so with binary, it's ones and zeros. So you can think of each position in the number as the 0 or 1 bit you can represent as on or off, the 1 bit being on, the 0 bit being off. Each position starting from the right would be 2 to the n, where the positions are going to be starting at 0. So the first position here would be 2 to the 0, with the 0 bit meaning off, I guess, if you would like to think of it in that form. Similarly, continuing on, this would be 2 to the 1, this would be 0, 2 to the 3, 0, 2 to the 4, 0. Oh, my bad. I skipped over those. But my point is each position is going to be a power of 2, and we can think of the 1 bits as being on or off, 0 being off in this case. So then looking at hexadecimal, which is typically what you'll be seeing ciphertext given to you in CTF challenges. Similarly, this is just another way of counting. Rather than base 10 or base 2, we're counting in base 16. So for our numbers that exceed 9, we'll be using A through F, where A is 10, B is 11, C is 12, and so on. So a popular number that you see come up in CTFs just as like a joke or something in like poem challenges I've seen before is OX dead beef. I don't know if there's any meaning behind that, but it just comes up, and that was an example I was going to use. So for both of these data representations, we can demonstrate how we can convert this from strings and back and forth. So one thing to remember in this case is that a character is typically 1 byte. So, and this being 8 bits right here, we can group these together, convert that to a char, and that's typically how you would be rebuilding a string for a CTF. But more typically, you'll be seeing hexadecimal. So in that case, since each character in hexadecimal is going to be 4 bits, we'll take 2 characters of hex, and we can group those together. And from there, you can convert those back to ASCII, because each ASCII character will be corresponding to 1 character, being 8 bits. I'll go through a few examples of this once we finish the slide. And then the last, it's not really a data, well, it's a data representation. It's an encoding format that sometimes you may see in a CTF. It's base 64. The one giveaway that it can be base 64 is that you will typically see trailing equal signs, which are how the format uses to pad in the case that it needs to. I believe it's 1 to 2 or 0. So it's 0 to 2 amount of trailing equal signs. So it's, if you see that, it's a good giveaway that it's base 64, just for any generic CTF challenge as well. But in the chance that the ciphertext is given in base 64, you'll have to convert that before doing any computation. So now I'm going to switch over to my other scene. So does everyone have the Git repo for this? If not, I can drop it in here.
Yeah, I'll drop it in the chat for you.
Okay, thank you.
Here it is.
Oh, sorry, I'll fix that.
Your whole OBS screen size seems a little small. I'm not sure if that's easy to fix, but I don't know.
The whole scene?
Yeah.
I
don't
like.
Yeah. Don't worry about it. Yeah. Oh yeah, there you go. That's fixing it.
So I'll give you guys like a couple seconds to go grab that. Okay. there a way I'm able to copy and paste into this to grab mine?
It's sometimes iffy. If Control-Shift-V or normal keybinds aren't working, then probably not.
Okay. So I will then. I'll just cast this then. So I'm just gonna put it side by side for now, and then you guys can follow along if you have it local or however. So for the first one, looking at the challenge text, I just put a few different conversions as well as a Caesar cipher in there. Just gonna go through how you would go about converting these. So for binary, the way I would usually do it is if you have, the first one is this for the first character. So usually I like to convert it to an integer and then just straight away to a char, as well as you can use online tools. So if I do this prefix, this prefix being binary, you can just wrap it in char here. First, that cut off. Sorry, that's the first one. So you can repeat that for all of them. It would be the same procedure where you can convert it to an integer using this prefix, and then the char, when you wrap it with an integer in Python, will convert this to a char. Converting the whole thing says ones and zeros, which is what binary is counted in. The next one for hex. So let's see. I'm just gonna try and grab this so I don't have to type it in. Then I'm gonna close this one. Oh, you still cannot paste into this. Okay then.
You should be able to use middle click. You can highlight.
Middle click? Okay.
Yeah, you can clone it.
So for these, so same thing for binary, as I said. You can convert it to an int, then wrap it with a char function to get the chars back. So in the case of hex, what we can do, the way I like to do it is I will use a byte array. So byte arrays in Python are a data type. We can create an array of them. Conveniently, when you loop over the byte array, you're able to have an integer representation rather than a character, so it's quicker that way, I find. So we can say byte array dot from hex, the method from hex, and then we'll take the hex over here, and then simply enough it converts it to this, and then in the next example that I'll be doing after this, in regards to XOR, using this sort of representation is very convenient because when we loop, we don't have to do any unnecessary conversions between chars and integers to XOR them. Rather, we can use a string, and then using the byte array, we're able to get the integer representation. So the other ones, base64, again, it's just an encoding format. I'm just going to show how to do it in bash. So what we can do in bash is we'll echo this string back, if it'll let me copy it. There you go. So echo, all it's going to do is the same thing as like a print function or a cat function. So when we give it that parameter of that string, it's going to echo it back. So then we can take the output of that and send it to another function, which is what we're going to do here. And that function in bash is going to be base64. So then we'll use the -d, meaning decode. When we do that, we get this back. I know this is an encryption, but I figured I'd show it. So you can do that. Similarly in Python, there's the bin ASCII library. You can use that to decode between base64. And then the last one on here, which is the example that we went through earlier, is a Caesar cipher. So my preferred tool for doing like classical sort of stuff is for Caesar ciphers. If I am aware that it's the Caesar cipher, I like to use rot13.com. So then you can copy it.
Chicken candy. I don't feel like making anything. I'm studying for 3 hours. I want to blow my brain.
Oh. Someone in the chat said Vim is a key combo for rot13. Not aware of that, but it would let me copy and paste. This website is convenient because you can run through different permutations where we're shifting by different variations. So in this case, I use a shift of 13 like I did in the example. But if you have other, if you want to try other shifts, you can use any of these. So moving on to the next ones. So after going through different ways of representing data, we can now talk about XOR. So XOR, typically you'll see it as this sort of O with a plus in between. Otherwise, you can see it as a caret symbol, or this is, I also have the symbol for a logic gate, if you're familiar with like a hardware, digital logic design kind of background. So XOR is a bitwise operator. we can also think of it as addition modulo 2, which is, you can kind of see that from this truth table here. So in any case where we would have the addition of 0 and 0, obviously we'll get 0. 0 and 1 in either case you'll have 1. 1 plus 1 mod 2. 2 goes into 2 even amount of times, so then we'll obtain 0 there. So it's just a different way of thinking about it. There's actual math that goes into why it, or how it can be thought of as that. If you're interested, it's with Galois fields and such. So the XOR operator has certain properties. So it might have been obvious from the last couple slides, these properties, but it's just convenient to go through because certain times and challenges, if you're solving with XOR, it's just convenient to know. So anything, a variable x XORed with 0 will be itself. So in the case that it's 1, 1 XORed 0 will be 1, 0 XORed 0 will be 0. Anything XORed with itself will be 0, so 1 XORed with 1 will be 0, 0 XORed with 0 will be 0. And then this is just showing distributive and commutative properties. So we can XOR 3 variables, x, y, and z, in any order that we choose, showing that we, and similarly for x, y, or x XORed with y, XORed with y, this is just a combination of the prior ones. So we're showing that anything XORed with itself here will be 0. And then as from this one, x XORed with 0 will be x. So you might be wondering, how is this useful? What can we do with this? So what we can do is what's called a one-time pad. So it's thought to be impossible to decrypt, and it certainly is very, very difficult if you even try, if these following constraints are followed. So for it to be that secure, we need what is a truly random key. There can't be any correlation between bits and such. If like you're using a pattern to determine them, that wouldn't be as secure as something truly random. So we need the key to be the same length or greater than the message, such that there's no repetitions of the key in the message when we XOR, because in that case, if it's small enough, you can just brute force it, or if there's known plain text, it might be simple to extract to just the key. The key can't be reused. This one is a little harder to see, but with known key reusage, you can, there's a variety of tricks that I've seen that you're able to sort of piece together what it can be. And then the fourth constraint, similar to the other ones, is you can't have known aspects or portions of the key be available to a third party if you want it to be as secure as promised. Similarly, if there's portions of known plain text, in the case of CTFs, this might be the case if you know a flag format. Like if you know that the flag format is the word flag and then curly brackets, and then inside the curly brackets is some sort of message. If they repeat the XOR key over that, you might be able to extract that key and then decrypt the rest of the message if it's not long enough in that case. So if it's violating this one and this one, it might be trivial to decrypt that message in that case. So the way we encrypt with this is if we've generated a key with the prior constraints being followed, or not in the case of some CTF challenges, we're going to XOR the message and key together. So it's a bitwise operator. So we're going to be taking each bit corresponding to the same position in the plain text and the key. We'll XOR them together. The resultant of XORing each corresponding bit in the plain text and key will be the ciphertext. So we'll go to now the other demonstration with so it's in the same repository, just in the XOR folder. So you can look at the challenge.txt file. It says, can you find the character I exited this entire flag with? Gave you the flag format here. So I used a single character, iterated over this message. So each character in the message was XORed with one specific character for each character in this message. So I'll give you guys a couple minutes to try it out, think of some approaches, and then I'll go through it. So to do this, you'll probably want to be using Python. I think there's online tools you can use as well if you prefer that. So I'm gonna slowly go through the solve for this. So we know that it's the message. We're using a single character, XORing each character in this message with the key being one character. So what I'm going to do to start is take our ciphertext, use a byte array, import the string, which is the hex string, which is the ciphertext from before. What I said before about using known plain text, so we know that the flag format, because from here, the flag format is flag, curly bracket, some stuff in between, and then another curly bracket. So we can leverage that, and we can say that our key is going to be equal to the first byte XORed with F. So we'll do key. So key of 15. So then, assuming that we did that correctly, we can iterate over the entire ciphertext using that key, XORing and getting the result being the message. So the way that we would do that would be, we can say for element in C. So what we're saying here is for every byte in this byte array, we want to access it, which will be element in this case. So we'll just create a temporary variable. We'll say element XORed with key. In Python, we use the caret symbol to denote XOR. So then from there, what I'll do is I'll use print. I'll say chr var. Oh wait, my bad. And then hopefully this Python version is new enough that that end equals will still work. Yep. So I'll put a new line there just so it's more readable. So doing that, we obtain the original flag back, being flag single byte XOR. So just to recap, we know that the flag format, being flag, starts with F. We can obtain the key from there because we know that the single byte XOR, when we take the original byte from the original first byte of the message, and we XOR it with this singular byte from the key, we're going to get the first byte of the ciphertext. So on doing that, we can say C of O, which we have here from the byte array. We can say C of O XORed with what we believe to be the first byte of the message from the flag format. So we'll say with F here, and then symbolically what this is going to mean is we can take this representation of C here being message, the first byte of the message XORed with the key. So we can substitute that in for C here, and then what that would look like would be key XORed with F. And then this turns out that our assumption was correct, because in this case, if you remember from the XOR properties, the first byte of the message is going to cancel out in effect with the with the same value of the flag format. So then we'll obtain just key in this case, and then using that key, we're able to iterate over the rest of the ciphertext using that key. Here we get each independent message of the byte, or each independent byte of the message, and then we convert that to a char. We use the end equals quotations delimiter just so that when I print it, each character will come out on the same line rather than a new line, and then that's how we end up solving that. If you're interested, I wrote an additional solve. It's the same thing, just maybe more explanation. And here in the write-up, and then the solve is going to be pretty similar to what I just wrote. So then now for the remainder. So what I'll be going over in day 2, we'll do AES, RSA, little overview of different more complicated crypto systems like elliptic curves, which is ECC, lattices. Those are 2 topics that I'm particularly interested in. But yeah, and then we'll do a brief overview of RSA. So RSA is a pretty widely used crypto system. It relies on the fact that factoring integers back into primes is rather difficult, especially when you use rather large numbers with a high amount of bits. So the way this works is we're going to, in a textbook case, this is not always going to be how it works in practice. They'll probably implement padding of some sort. So the way it works for textbook practices, we have 2 integers, p and q, that we are going to select to be primes. We multiply that together, giving us our modulus n. And as I said before, this is the whole underlying message of, or the reason why cryptography is a secure thing, is that we introduce hard problems which are difficult to solve, in this case being factoring an integer back into its 2 primes, or sometimes in the case you might see in CTFs, you'll see multiple primes, maybe 3 or even as many as you can count. But then, yeah, so we have then 2 key parameters, E and D, E being the public key, which is what you'll what you would send in a transmission, and then each party will have their own private key. So the key thing here, which we'll go into more detail about on Friday, but the values E and D, we choose them to be what we would call modular multiplicative inverses. All that really means is that when you multiply these two integers together, they're congruent to 1 under this modulus n. Why that is, we'll go into that more on Friday. But then with our message m being some value, which we'll take that message as an ASCII string, and as I said before, we'll do some conversion to a numeric representation, which we can use to do computation. So the way that we would encrypt that would be we take our message and our public key, we raise our message to that public key, and then we can say that that's congruent to C modulus n. And then similarly, when we look to decrypt it, we'll take that ciphertext from here, take the private key, and raising C, oh, that should be a D, my bad. C to the power D is going to be equivalent to M to the power E times D, because note that when we encrypted, we took M to the power E, so similarly, we can say that the ciphertext is M to the power E, and then when we raise it to what should be a D, that's the same as saying M to the E, multiplying E with D there. And then remember, since we chose them to be inverses of each other, that result will give us back M modulus n. And yeah, so that's pretty much it. Does anyone have questions in regards to that?
Thank you very much, Brandon.
Yep,
Tune back in
thanks.
again Friday for day 2 of crypto. For you Boilers people, good job playing Seesaw this weekend, and everyone else who played Seesaw. It was fun CTF. Little on the gassy side as we would have hoped, but still Seesaw. No Twitch plays. Our bootcamp CTF is in 4 weeks, so remember to sign up for that at play.ctf.boilers.com. I try to paste that link in the Slack, assuming that's the correct link. Yep, not Slack, in the chat. Sweet. Talk to you guys again next week. Enjoy your weeks.